Welcome everyone to today's episode of Iron Beetle, a show where usually we look at the source code of Tagabeetle, how we could implement a database which is super reliable, which is super fast, which doesn't allocate memory, which is implemented in Zeek, and which is thoroughly tested through deterministic simulation. But today, as promised, is going to be a special episode. It is going to be a non-technical episode where we discuss technical values of Tagabeetle. Like what are the underlying principles, what are the underlying guidelines which tell us how to write software in this style. And as this strays very far from our usual genre, I want to be like very upfront. So today, no coding, only philosophy. So if you are not into like blah 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 soft philosophical stuff, then please don't watch the stream, but go and watch the bonus stream from earlier this week, which is available on YouTube, where we go into much more technical topic of how you can safely hand off durability from write-ahead journal to our snapshot on disk in such a way that at any point in time you maintain enough physical redundancy to enable recovery. So, okay, yeah, let's get started. I'm not sure if I need to, well, okay, I will share my screen just in case, because, well, the picture is prettier than me, but I'm mostly going to be just talking and wildly gesticulated. So, Tagabeetle's technical values. Those are pretty straightforward. Let me zoom in a couple of times. This is our values: safety, performance, experience. We want Tagabeetle as a software to be correct, to be safe with respect to the task it actually does in the world, tracking, accounting, tracking transactions. We want to be it to be very fast, and we want to delight our users. We want to make it easy to use Tagabeetle. We want Tagabeetle to not be a thing which creates dread in your inner soul. So the question is like, why those three values? But before that, I'd love to discuss a higher level aspect of that. Like, why do you need engineering values at all? Like, I mean, you could take clean code, you could take Gano 4 pattern, And okay, and the Twitch stream stopped. So let me understand why is this happening and whether I'm online at all, because I should be online, because this time I am actually calling from Sweden. Okay, I'm back. That's great. And just in case, let me... Okay. Yeah. So hopefully I'm back for good now. Yeah. So why have technical values at all? Why can't you pick some good books about software engineering, like, I don't know, GANA 4, Patterns of Enterprise, Software Architecture, Clean Code, whatever you like. I just like, go and code. And I think like the principled answer for why, if you want to implement a large program, you like need to think about this like soft stuff like values, is contained in this like very good quote by it is from Google, that software engineering is programming integrated over time. That is, whenever you write a program, whenever you build software, there is always an inherent time dimension. It's not only about what you're coding today, but it is about how the code you're producing today is going to be used 10 years from now. And this actually creates a lot of constraints on how you engineer the software. So I guess to zoom onto this, like the most commonplace, the most like visceral phrase you hear, which explains this idea that software has a time component, is this idea that over the lifetime of the software project, most of the costs are concentrated in the maintenance. So it's not too expensive to write the software, but it is very expensive to upkeep the software, to maintain it. It's important to realize that there is also a flip side of it. It's not only the costs of software, which are spread over time, it is also the benefits. This is like very important thing. When you write any software, most of the benefits that this software will provide to the world are actually in the future. So, for example, 5 years ago, I was writing various IDEs for Rust. And at that point in time, Rust wasn't all that popular, and few users actually used my software. So kind of like it had some users, it had this very crucial feedback about whether it is useful or not, but in the absolute sense, it wasn't actually providing that much value. And today, once I actually stop being seriously involved with that software, it only starts to provide the real value, because, well, now number of users of Rust is much bigger. So that is the thing. When you want to like not only write a program, but to implement a software system, you really need to think mostly about the future, because it is the future where both the costs and the benefits of your software are concentrated. So this is one aspect, why we need values. The second aspect is that is captured by that another famous blurb of text, that famous Gerald Spolsky post about how you should never ever rewrite the software. And again, from my experience, this is kind of like even more true than that post implies. So it's not that like you shouldn't rewrite, but most of the time you actually cannot rewrite, because there is a lot of path dependency in the software. And if at some point you realize that you want to change it drastically, I mean, you just cannot do this, because the existing software gets ossified around the existing architecture, around the existing use cases. And if something new comes along, you often cannot really integrate this into the existing system. So in this sense, I like to think that the way that the large software systems evolve is that they are not changed, rather they are challenged. So at some point, an existing software system faces new requirements. Or there is like some realization about how to fulfill the existing requirements in a fundamentally better way. But that system usually is not really possible to change. So what happens is that someone builds a new system alongside, like completely divorced from the existing one, and that system is a challenger and then just wins over the relevant market. So these are the two forces which you need to think about if you design software systems. That first of all, the benefits of your system are going to be concentrated in the future, the value, and the cost as well. But at the same time, the decisions you make today, while you know very little about the future, are going to be very sticky. It's going to be very hard to course correct once you already have the body of a software. And that is the challenge. That is like why large scale design of system software is hard. You need today to make decisions about the future which you cannot easily reverse. And luckily, there are two very powerful tools which help with this aspect of software engineering, and that is like CNC of software engineering, compiler, and culture. So let's start with compiler. In one of his talks, John Carmack, the Doom guy, made a very pointed observation that if you have sufficiently large code base, then any code pattern which is accepted by your compiler is going to worm its way into this bigger software. Basically, if this is accepted by the compiler, you're going to find this in the wild. It's just going to happen. If you are not finding this, well, either you're searching poorly or your software is not large enough. This is kind of like fun observation. Actually, is connected to rather profound and rather complicated mathematical fact, the Kolmogorov 0-1 law, which says that hey, if you have like infinite sequence of events and you formulate some predicate about a subset of these events, then the probability that this predicate holds is either true or is either 0 or 1. So as long as you repeat something enough times, then any particular like subproperty of a sequence of events is either guaranteed to happen or guaranteed not to happen. So yeah, in terms of software, this is really about like what your compiler accepts. And actually, I have like fun anecdote there where I kind of like very viscerally realized that yes, this is like very much true. I once fixed a bug in the parser of a Rust compiler, which was, well, just like parser accepted some obviously incorrect code which shouldn't be accepted. Just some like, I don't know, like it was like, I don't know, duplication of like some kind of like punctuation or maybe misimplication. Like I don't remember the details, but basically, yeah, obviously wrong code. And I actually failed to learn this code very quickly because it turns out, well, not only the parser of the compiler was buggy in accepting this erroneous and completely bogus code, but the actual compiler contained one instance of this syntax error. So yeah, kind of like you need to have compiler to get certain properties of your software, which you can maintain over time successfully. And one may think that, okay, so let's develop this idea and let's extend it and let's use this to fully solve this problem of software evolving over time. So for example, you could say that, well, compiler is just a static analysis. And more generally, it is a way to test a property of a source code automatically. So what if we do an extended set of checks? what if we essentially have a test suite which nails down the behavior of our software, and then we can be sure that, hey, we are writing a test suite today, but 10 years from now, this test suite will still guarantee that our software maintains all the same properties that the test suite originally enforced. And that seems like a nice idea, but that very often clashes with this second C thing, with culture. Because what could happen is that at time t, you have a test suite which is very good. It is fast. It helps you to evolve your software faster. It guarantees a reasonable degree of correctness. And then someone, I don't know, maybe a more junior developer, or maybe someone who is just not accustomed to this rigorous discipline of testing, adds a new test, which is kind of like not a bad test, but it's slightly worse test. So for example, it is slow, or maybe, it like fails with like probability 1 to 1000. So if you run this test 1000 times, like one time it will fail. And let's assume that actually nobody minds that, and you have this like perfectly fine test suite, and then one test that is just slightly worse. What could happen next is that at some point someone adds a second test, which is not as great as the baseline which we've started with. And the average quality of test suite is going to trail down a little bit. And if you start continuing this over and over again, you might end up in a situation that even though you started with a very good test suite, you actually ended up with a test suite which is much weaker, which doesn't provide as much guarantees, which is like very annoying to run because it takes ages to run, and they're like flaky tests and whatnot. And at some point, someone will say, okay, so actually those tests are not that useful. Let's maybe disable them, or maybe let's get rid of our not rocket science rule because it prevents us landing pull requests quickly, etc., etc. So yeah, the reason why those things happen is because you have like a certain engineering culture, which has like very keen sensitivity to what things we do and what things we don't do. And you really need this culture thing to make sure that it is maintained over time. And in particular, this actually extends to the compiler, because like the difference between the compiler and tests is that the compiler is maintained externally. And even if inside your particular team, you could slowly regress your culture, regressing compiler is much harder because compiler is managed externally. You cannot, just argue with compiler. But even that, at some point someone will say, okay, let's allow warnings from the compiler because, well, we already have a lot of warnings and they kind of like get in the way, so let's not fix them. Or maybe at some point someone decides, okay, that's like too strict semantics of the language. Let's maybe use some lax flags which prevent some optimizations, but allow us to write like more questionable code, which is like hopefully not undefined behavior. So even for more hard things like the compiler, still the engineering culture is the primary thing which allows you to maintain those properties over time. I guess the great metaphor for culture is a river, because like imagine a river, like there's like a lot of water, and this water flows, and it flows in a particular course. It flows in a riverbed, and at times this water might be disturbed. So for example, if you have a lot of rain in a particular week, or if there is a spring and there is like snow thawing, you might get more water than usual, and then you get a little bit of flooding, kind of like a river slowly moves out of its usual course, but in a very short, limited amount of time, the river will be back. So the flood will pass, the drought will pass, the rains will pass, and the river, like over medium time, will actually flow more or less the same way. But if you zoom out a little bit, and if you look at this river for, say, a decade or a century, you might realize that, hey, actually, while the river is flowing, it tends to erode its banks. It tends to erode its bed. And over a long period of time, it tends to change its course. And this is how culture, like any human culture, in particular engineering human culture, works. Locally, it is very stable in a sense that it is hard to change. And if you apply any external pressure which moves the culture, it will bounce back. It will get back to where it was. But if you think over the long-term horizon, then the culture is also malleable and it can very well change its course. So tying that back to software development, if you are designing software and your task is to design something which will be impossible to change in the future because the gravity of the existing source code is too high, but at the same time, most of the value is also going to be concentrated in that future. Managing culture, managing this like implicit rules of how you do things is the most powerful instrument available for you. And the role of values, of principles in this example is similar to the role of dams and canals when we speak about the rivers. So they kind of like, help to direct the river towards productive usages. They help to keep in check that effect that over a long period of time, the river tends to change its course. So yeah, this is a very long-winded answer to why have engineering culture, why have engineering principles, why have engineering values. Now, let's get back to specifics. These are the three things which we consider to be the core technical values of Tiger Beetle. Safety, performance, and user experience. I cannot type. Okay, yeah, now it is a little less embarrassing. So why those three things? Well, let's start with safety. If people use Tiger Beetle, we want to make sure that Tiger Beetle will store their data correctly. It will never lose data. It will never make an erroneous computation. It will never say that, hey, at one point the transaction happened, and at a different point that, hey, actually this transaction didn't happen. In some sense, you could think about safety as like, just correctness, although there is like important subtle difference because it's sometimes you can be incorrect in a sense that you crash, but crash can still be a safe behavior because it's not actively malicious. So we kind of like care about all correctness, but we especially care about safety. And the thing here is that everyone cares about correctness. Everyone cares about safety. If you pick some random programmer on the street and ask them, hey, do you want your software to be correct? Do you try to make your software correct? They answer like, yes, of course. Yes, I'm like, correctness is like important, testing is important, static types are important. And I think that while like, to the first approximation, this is true, everyone cares about correctness. The truth is actually slightly more nuanced. I would say that it is not true that every software needs absolute correctness. Most of the time, you actually want a balance between usefulness of software, its features, and the amount of correctness, the amount of bugs it has. So kind of like you want software to be maximally useful and not too buggy at that. One very specific example here is, for example, Rust Analyzer. Because Rust Analyzer internally is explicitly engineered with the idea that the code itself is going to be buggy. That's why in a couple of crucial pieces in Rust Analyzer, there are cache panic calls, which make sure that if some code completion or some refactoring is buggy, then only that single completion variant or only that single refactor crashes but the rest of the system continues functioning normally because this is more helpful for the users. They still can use all the other features which are not buggy, and they can just ignore this single buggy one as long as it doesn't actually crash the whole process. And if you think about it, this is actually true about like more or less every software. I mean, like I open a browser on my mobile phone, and like on some web pages, it just crashes, it dies, which is okay. Yeah, it's not good. It would be better if it didn't crash, but it's actually not that much of a problem for me because, well, I just restart it and I open a different page and it works. And it is important to realize why this strategy of failure isolation works. On the deep level, this works because you have a database. So a solution to every crash is a reboot at some level. Let it crash and restart it. Restart the thread, restart the process, maybe like, you know, if you're unlucky, restart your computer or like reinstall your operating system. But what you can be sure is that you are not going to lose your data. Like, I mean, if you if your browser crashes and then you reopen it, well, you know that all your email history is still back there. This is the failure isolation, and an important thing to keep in mind when you think about Erlang's philosophy of let it crash, because there are always two components there. One is that you let it crash, but the second component is that there is some larger software system which holds your data and which continues to hold your data even if you crash. And now you kind of like see why safety is so important for TigerBeetle, because, well, that system which keeps your data safe while everything else crashes is the database. And TigerBeetle is the database. And what's more, it's a financial database on top. So for us, again, as everyone else, we say, yes, safety is important. Yes, correctness is important. Yes, we care about safety very much. But unlike most of the software projects, we actually don't have some larger, bigger, more reliable system which we can fall back to provide fault isolation. We are the last line of defense. The overall reliability of the system, like the lower bound on the upper bound on the reliability of the overall system, is defined by the reliability of the database. So that's why we put safety first. Okay, so safety is our most important value. The next most important value is performance. And I kind of like said that safety is first. I take this back. I would say that performance is actually our first value. Safety at the same time is our zeroth value, but performance is first. And why is that? Well, if you think about it, computers are fundamentally about speed. There is very great post by Grayson Hoare about how, like, you know, like how fast your crunch numbers is actually the essence of computing and why we are in this business. Because, well, you know, there is nothing a computer can do better than a human. The only benefit of a computer is that it can just execute everything much, much faster than a human or even a bunch of humans. And kind of like, you know, if safety is the value which we use to differentiate in a qualitative way from other systems, then performance is like, you know, our level. Like performance is where we can actively benchmark and where we can actively get better, faster, and where we always are looking for improvements. And a reasonable question here is like, okay, so yeah, like we are all engineers, we're all programmers, we write optimizing code, we like writing code, we like low-level languages which allow us to use like seamed or like async or whatever. But is there actual, you know, real world need for performance if you think about transaction processing? And again, as with all things real world and with all things programming, the answer here is that we don't know, because again, everything that is of importance happens in the future, and we can't say for sure what the future will hold for us. But yes, we are making a pretty significant bet that the world of accounting does need improved performance. And there are two aspects of that. One is that there are a lot of people in this world, and there are going to be even more people in this world. And moreover, there are whole countries, whole continents of people who currently don't have access to cheap, great financial services. And well, we are all optimists. We think that, well, in the future, actually, more or less every human on Earth will be living a rich life, like things like hunger, lack of basic housing, whatever. Like we are going to solve this, and this will increase the number of people who actually, well, need to transact, need to track various things, money, but not necessarily money. And that is where you like really need performance to move beyond just Western world. But that is actually a minor reason for why I think performance is the key. Because, you know, there is an even deeper effect there. And I kind of like maybe somewhat provocatively call this induced demand. So induced demand is like idea in economics, or at least in like quote economics. And this comes from like this parable that you have a highway, and the problem with the highway is that there are a lot of traffic. If you actually use this highway, it takes you ages to get where you want. And well, at some point, people figured out that, hey, the solution to this traffic problem is to make the highway wider, and they did that. And then they observed that actually traffic didn't really get away. So with highway wider, there are still traffic jams, simply because now more people use the highway. And kind of like, you know, the first order thinking here is that, hey, it seemed like people needed a highway, so we built more highway, and now people need highway even more. So like, you know, building roads like doesn't help with traffic congestion, because if you build more roads, then people just consume more roads. So let's do something else. But it's important to look at the second order effect here, because, you know, roads are never terminal goals. We are stuck in a traffic jam, not because we like being stuck in a traffic jam, but we are doing this because we want to get from point A to point B, and there is like something very valuable at that point B. And when you make a highway wider, you actually make commuting from point A to point B easier and cheaper. So you increase the value of that area B, and then people build there more housing, they build there more factories, they build there more offices, parks, whatever attracts people. And so that increases the value of that parcel of land, and more people want to get there, and that is why you get more demand for a highway. Not because, like, you know, it just creates demand out of thin air, but rather because it actually makes the stuff on the other side of the highway more attractive. And, you know, kind of like this is nice second order explanation, but like, you know, if you just take a highway and then build it twice as large and then twice as large and twice as large, you will end up in a world paved with concrete. So kind of like making the highway wider is 2x solution. You just make something twice, you increase capacity by doubling it. But there are sometimes ways to make things drastically cheaper. For example, instead of building a second highway or making the same highway twice as wide, you could actually put a rail line along it. And then using a railroad, you can actually transport the whole batches of goods and people very cheaply, because, well, one train is able to move way more people and goods than an equivalent bunch of cars. And by using a railroad there, you actually increase the capacity not by doubling it, but by making it 100 times larger. And this is the core insight of TigerBeetle. Literally, like, let's use the railroad. Well, like, actually, there are two different insights, but they both apply to TigerBeetle. One is that, hey, if we make tracking transactions couple of orders of magnitude cheaper, that would actually unlock more use cases for tracking transactions. And one very great example here is, for example, green energy. Because the thing with green energy is that it has very high variance over geography and over time. Like, you know, it is like very hot in Portugal today. There is like a lot of sun here, but for example, in Sweden, the country where we actually are making this call from, probably it is not as hot today. And yesterday, it was quite a bit colder here and quite a bit less sunny here still. So, you know, if you want to use your green energy efficiently, because the energy is very expensive to store, you need to be able to move the energy from places where there is excess supply to the places where there is excess demand at a given point in time. And the more efficient you can track this supply and demand, the more efficient your energy gets. And the thing is, like, energy is continuous. So you could track energy use once a month, or daily, or every hour, or every 5 minutes. And of course, there are diminishing returns there, but generally, the finer grained your tracking is, the more efficient your system is. And well, if you have a system which can track these with like 2 order of magnitudes more throughput, then you could cut maybe your electricity sampling interval and then increase the real efficiency in electricity consumption. And the second thing why the train railroad metaphor is so apt when we apply to TigerBeetle is that because this railroading, this train thing is literally what we are doing. The main idea for performance of TigerBeetle is to batch things, not to treat each transfer as an individual car which needs to move through the consensus algorithm and then through the storage and then through the state machine, but rather to take 1,000 transfers, put them into the same train car, into the same wagon, and then move them all in a single batch so that all the costs are amortized and you can apply the actual processing very quickly. Again, the second reference to Graydon's talk this time, it's a blog post, is the talk about vectorized interpreters, which, well, the source of this train metaphor. Because yeah, this is like one of like the cross discipline core ideas of how you could make something couple of orders of magnitude more efficient. You do this by batching. You do this by amortizing costs across many individual instances of a problem. Okay, so that is performance of TigerBeetle as an engineering value. And finally, user experience. So this is very interesting. You see, if we speak about performance, if we speak about safety, then those values are directed internally. They are very cool when you talk to other programmers, especially, believe me, if you talk to other programmers who also work at TigerBeetle, because like we understand those things like very viscerally. Like we kind of like can argue about like, hey, why our like batch architecture is like how you actually build fast systems. We can explain why we need to account for storage fault model to actually deliver safety of a distributed system. But you know, basically everyone like cries about those issues. Like everyone screams how, hey, our database is the fastest, our database is the safest. And sometimes this is more true, sometimes this is less true. But to actually figure out what is the case, you need to spend your time. And like we all have lack of time. Time is a very scarce resource. So it's hard to like figure out like which of the 10 different databases you should take a look at. And this is where user experience comes in, because really what solves this problem is joy. If people just like using software, they can tweet about it, they can tell their friends about it. They don't feel that they need to spend their energy when they interact with the software. On the contrary, they might feel that, hey, like actually it's fun hacking with this particular programming language, so I'm going to spend some more time, and then I'm not going to feel tired, but rather I'm going to feel energized because yes, the thing is so good. And this is our third engineering value, user experience. This is basically helps us to explain to people why we are so cool, not in a boring way, but just demonstrating this by kind of buying some credit that, hey, actually, well, our binary fits on a single floppy disk. So that is kind of cool. And if you might want to learn more about like, hey, how could you build a database that fits on a single floppy? Well, then you might read something about like safety, performance, and realize, hey, actually, using Zeek and not using allocation after startup, it's kind of like cool. And also there is like this NASA's power of 10 rules and deterministic simulation and all that stuff I've been discussing for the past 32 something episodes. And again, I love to seek parallels with the Rust programming language, and I have a feeling that this is actually very close to how Rust programming language ended up in a place where it is today. Because I mean, when I started working with Rust, and in some sense even today, I kind of like think of Rust as a better C++. I think that the reason why Rust is a big deal, because it is a C++, but it is safe. So you could have the same amount of performance, the same amount of control over memory, but also you are safe. And this is like freakingly cool. But at the same time, it is hard sell for people, because relatively, I emphasize this, relatively few people actually code C++, because kind of like higher level programming languages took over the world and everyone codes Java and Python and JavaScript. So I don't think that, well, while, hey, Rust as a safe C++ was an important, was like a crucially important sell and like the real value delivered by the language, I don't necessarily think that that is the main thing which managed to sell Rust the wider audience. Because I recall this historical evolution of Rust, there was a lot of excitement in the form of, hey, Rust is like Ruby, but it is fast, it has a compiler, and it which checks for errors, and it has some types. And I mean, like Rust as faster Ruby with static types and some types. I wouldn't say that this is like the core value proposition of a language. It is really like it's like C++, which is safe, but this is, hey, you could use Rust for high-level language stuff, is what people took and what people run with it, because, well, this is user experience. This is delightful. I mean, like Cargo is great. RustMET is great. Having like all those kinds of tools, having like this language which actually tries to be helpful to you, language which gives nice error messages, is what makes you love a language, what makes you use it more. And only with time you actually get to appreciate that, hey, actually this is also a C++ which is safe. And to kind of like continue this metaphor even more, I think that induced demand thing also applies to the Rust case, because again, when I was starting with Rust, I thought that, hey, the real domain of Rust is like where people currently use C++. But I think that what actually happens is that a lot of cloud software, which could have been written in Java or C# or Go or maybe even Node.js, ends up being written in Rust. And the reason for that is that once you have a programming language which is simultaneously memory safe and at the same time very fast, as in it doesn't have garbage collector and allows you to have tight control over your memory, you actually realize that a lot of problems for which the standard solution was a garbage collection language now can be solved in something which has better runtime characteristic. And that essentially opens up new areas for application. So the other big reason why Rust is such a successful language is that it increased the size of the systems programming domain. Now, much more things are systems programming because, well, in Rust, actually everyone can do systems programming and not worry about shooting themselves in the foot too much. Okay, so I think that is more or less everything I wanted to share with you today. So to recap, safety, performance, user experience, kind of like the things which make targetable. And the reason, well, again, maybe this is all stupid. Maybe like this all like doesn't matter, and what really matters is like how you like just write code day to day, because it's it's like really hard to get any hard data. It's like really hard to compare targetable, which is developed today with these values explicitly specified. There's some alternative targetable, which is developed without any explicit reference to values, and like just a bunch of good classic books on the systems programming and programming in general. But yes, our hypothesis is that very much you do need these values to preserve these core properties of a software over time when you don't know how your software will need to evolve, but you know that any drastic evolution is going to be hugely painful. And for Rust, for Red Database, focusing on safety, performance, and user experience in kind of like that order, but also with an eye to try to find solutions which solve all three of them at the same time, is actually beneficial. And well, yeah, okay. Let me maybe pause from summarizing and emphasize this last bit, because this is actually very key part. One thing about the values is that they are ordered. If you have a trade-off, you kind of like need to throw safety, performance, or user experience under the bus. And for TigerBeetle, the answer is that if we are at that position, then we are throwing user experience under the bus first, and then performance and like safety is like non-negotiable. But it turns out that a lot of times, if you like look at the problem from a different angle, if you think outside the box, if you do something maybe stupid, maybe unusual, you can often solve like 2 of the 3 or maybe 3 of the 3 in one single way, which is just Pareto better than anything else. And one key component, which is slightly lower level than those 3 values, but which is often an instrument for delivering all 3, is simplicity. So kind of like, yeah, let's actually put this here, because this is really important. Simplicity. Like, if you strive for your software to be simple, you oftentimes can actually go and deliver on all of those values above. So, okay. Thanks for entertaining me with this very non-technical, very philosophical foray into higher level thinking about how TigerBeetle should be developed, what are our engineering values and principles. And next time, next week on Thursday at 5 p.m. UTC, live on Twitch and then recorded on YouTube, we'll continue with our usual stuff of picking TigerBeetle apart, figuring out how it works inside, and trying to find maybe any bugs there or any bits of code which could have been written better. And I'm not actually quite sure what is going to be the topic next time, but given that we covered Forest and the Groove the last official time, I think we'll maybe just bite the bullet and try to trace the right path from the state machine right to the disk. Probably will going to bog down somewhere at the level of a mem table, but we'll at least try to go that way. Okay, thanks for watching and see you all in a week. Goodbye.